This program is brought to you by Stanford University. Please visit us at stanford.edu.
Tad is originally from Poland. Got his PhD at the Technical University. Spent some time at the University of Minnesota before he finished his PhD, and then afterwards as a postdoc. Worked for Shell Oil in the area of basically enhanced oil recovery for a few years. Joined the faculty at UC Berkeley in 1990, if my memory serves me. So I'm doing salt from memory. Served me well in 1990. Originally in the Department of Material Science and Mineral Engineering, and then later in the Civil Environmental Engineering. I think that address is only good for a few more months because he will be going to the University of Texas to become the chair of the Petroleum and Geosystems Engineering Department in the office. So thanks a lot. Thank you.
Okay, so let me turn off the lights maybe. Well, first of all, it's a great honor to give this seminar, and it's a pleasure as well. I thought a long time how to give it to you in a way that would have some science, but also some policy implications. And I decided to talk about food and agrofuels and green revolution. And I would also like to stress that even though here in California, we seem to be fairly insulated from the violent events worldwide that deal with food and agrofuels, we're not. And this is actually UC Berkeley's own bear behind double chain link fence with barbed wire. And at issue are 50 oak trees that were planted there to commemorate the First World War veterans 90 years ago. And those blue containers is a company that wants to move in, sponsored by the university, to build a new athletic center for our professional athletes. But this is kind of a stage in which environment always loses when it comes to quote-unquote development, and now Berkeley is a case in point. And I would then tell you what this flag in front of the barbed wire says at the end. There have been slow changes in attitude surrounding agrofuels and surrounding food, and probably most of you have read this article by Michael Grunwald, who has been at it for several years in time, and then a week later or so, The Economist came up with this ominous-looking picture of a mega monoculture filled with one plant that is heavily subsidized with fossil fuels, and nothing else should grow. So this is kind of the future of the world according to Monsanto. But it was very difficult for people who were not in this area to actually understand the subtleties and the implications of the arguments on both sides. And one of the reasons is that the truth is triangulated, especially in the US, by the main media in a very specific way, and I'll give you an example. So suppose that I claim that 2 + 2 is 4, and suppose that you all here in this room agree to say that 2 + 2 is 22, which would make you biofuel enthusiasts. And then there's many more of you, and you are loud and you deeply believe that 2 + 2 is 22, so then the main media pick up the story, and it will go something like this. Most people now believe that 2 + 2 is 22. There are some scientists and engineers, however, who maintain that 2 + 2 is 4. As to economists, for them, 2 + 2 is 4, at least initially, but given enough time, it may become any number whatsoever. And so I am also a scientist, and in fact, my role in the last 4 years has been the role of Ned Flanders in The Simpsons cartoon, who said the following immortal line: "Science is like a blabbermouth who ruins a movie by telling you how it ends. There are some things we don't want to know, important things." And that actually is sort of the attitude of the general public surrounding this question. Just kidding. So I will run out of time, and Roland will remind me, so I'll give you a summary of my conclusions up front, and then I'll chug on as much as I can. So I've looked at food, and I've looked at main staples, which are wheat, rice, barley, potatoes, and rye. And I looked at a lot of statistical data, which I will summarize for you in a second. But these are my main conclusions. Well, first of all, the world production of these staples is not keeping up with population growth. That's certain. Their production is stagnant or declining, and crop areas are declining as well. Per capita production, that is kilograms of grain per person per year, and per capita yield, which is a funny number, I'm going to test your knowledge of science on it later on, which is kilograms per person per hectare and per year, a very small number, of course, are declining. And so, in essence, we are witnessing a global failure of modern food supply and the ensuing hyperinflation of food prices, and I will comment on that as well. I have also looked at main energy crops, and I call them energy crops because they are mostly used not to directly feed people, but to either feed animals and then through them people, or directly as sources of energy in biofuels or agrofuels, as I call them. So I looked at maize, known in the US as corn, sugarcane, soybeans, and oil palms. And as you will see, the world production of these crops is rapidly expanding. Their crop areas are increasing, and in case of soybeans and oil palms, in fact, they're increasing exponentially. Per capita production is increasing as well, but per capita yields are declining. I'll comment on it later on. So in essence, what we're witnessing here is a global move away from food to energy crops, and we are diverting more land to these pure energy crops as it is planned, such as switchgrass or miscanthus grass. And when we do, this will only deepen the global crisis of food supply and global ecological crisis. I will talk about agriculture in a very abstract way. So I want to show you a couple of pictures from my favorite satellite, which I've been using over the years to prove various points. This is the Aster satellite. And these are pictures 10 by 12.5 kilometers of fields in various environments. And so on the upper left, you are seeing a regular field development in Minnesota. So this is your mostly corn, perhaps some soybeans. The next panel to the right, you can see Nebraska, central pivot irrigation systems. So that's mostly corn, probably, maybe some soybeans. Lots of fossil water used to irrigate them. The picture that you see on the right is in fact a random field pattern very typical of Northern Europe. This one was taken in Germany, but I flew over Sweden recently and I took identical pictures. So what you see here are generations of division of land between parents and sons and grandsons and daughters and what have you, and the resulting mishmash of little fields. What you see in the lower left is development of soybean plantations in the Amazon, but not on the Brazilian side, as everybody would expect, but on the Bolivian side. So you have human settlements in these very large 5.5 and by 5.5 kilometers squares. Right smack in the center, you have a village, and then the fields are radiating outwards from it, and then you have some trees left behind. In the middle, you see the Thailand rice paddies. Thailand used to be the major rice exporter. They just stopped doing so. And because of it, the sub-Saharan countries now are suffering famine. But you see a lot of fine structure of rice paddies with lots of canals, very efficient agriculture, one of the most efficient in the world. And finally, in the lower right, you see very large field developments characteristic of the Cerrado, area of Brazil, which is east and south of the Amazon, were now mostly sugar large, and they were indeed globally, as I will demonstrate to you in a second. I will dispose of agrofuels in 2 or 3 view graphs and never come back to talk about them, because I've written enough. You know what I wrote, and if you don't, please read it. So the point I want to sell you on is that your mileage that you get in driving as an ordinary driver is in fact directly proportional to the energy content in your fuel, or energy per unit mass of your fuel. And so this was a road test done by Consumer Reports, where they drove 2 Chevy Tahoes of the same kind that Vinod Khosla is driving. One on E10, which is a gasoline that contains 10% of ethanol, and the other one on E85, which is ethanol that contains 15% of gasoline, roughly. And so the red points are the experiments, and overall those Chevy Tahoes got about 14 miles on E10 and about 10.6 miles on E85. The blue triangles are my calculations in which I calculate the mileage on another fuel if I know the mileage on the first fuel, given that the air-to-fuel ratio is kept at the optimum value by the car computer and the driver has not changed the habits. And so the bottom line here is that indeed how far you drive, if you're not an Indy race driver, depends only on the fuel content, on the energy content of your fuel. And since ethanol has oxygen in it, which more or less takes 35% of the molecular weight of ethanol, then you cannot further burn the oxygen, and that's why it has a lesser heating value. And also, I would like to point out that according to the the CAFE standard, which is corporate automobile fleet standard, that Chevy Tahoe was getting 35 miles per gallon when it was driving on E85. And of course, this would be stretching reality. So I'm going to just dispose of Agrofuels in this view graph in the following way. I'm going to give you an example of you driving a Chevy Tahoe. So suppose that you are a progressive young American and you want to drive on pure ethanol because it's good for the environment and it's good for the planet. But at the same time, you are a security-minded person, so you want to drive a tank, so therefore you're going to drive a Chevy Tahoe. And according to my calculations, you're going to drive it at 9 miles per gallon. And if you are a statistical American, man, woman, or child, you're going to drive 10,000 miles per year. Each one of us drives it, whether we do or we don't. And so you will need about 1,100 gallons of ethanol per year to drive your Chevy Tahoe. Now I'm going to give ethanol the following efficiency: 2.5 gallons of pure ethanol per bushel, no denaturant. That's a historical average efficiency of the US industry. I'm going to give it the silly fossil energy output that is ethanol to the sum of fossil energy inputs, which is all fossil fuels, of 1.25. That's sort of the average DOE number if you disregard the byproducts. And it makes no difference to my argument. You can stick any numbers you want to. But as a result, the following numbers come across very clearly. First of all, driving your Chevy Tahoe, you're going to burn food which has energy sufficient to feed 67 people in that year, 67 people. And because that agriculture, corn, and that ethanol in the ethanol plant require plenty of energy to be produced and processed, you're going to burn energy sufficient to feed another 54 people to produce the ethanol fuel. And so together, you're going to burn enough food or take out food sufficient to feed 120 people. Now, if all Americans felt your way and drove Chevy Tahoes, just like you do, we would eliminate food equivalent for feeding 36 billion people, more or less on 6 Earths. Okay, so that's not a good idea, probably. And as Mike Jacobson will attest here, you are very likely to emit up to 50% more greenhouse gases than from gasoline. And we can squabble about exact number. Again, makes no difference to my argument. It's a pretty bad solution. Now, here it's 100 people. This is a class I teach. And in fact, if you count all the heads here, there's 98 people here. So it's less than 120 people. It's a lot more than here. So this is how many people will not get food when you drive. Now I'm going to give you a little bit of history, because what we do today is in fact really predetermined in many ways on the things that happened in the past. So to illustrate my history, I'm going to plot percent of US population on food stamps as a function of years starting from 1970, 69. And the historical decision in the saga of agrofuels was undertaken by one Earl Rusty Boots, the second agriculture secretary under Richard Nixon, who changed agricultural policy of the United States forever. He essentially eliminated Roosevelt's New Deal policies of protecting the farmers and asked the farmers to plow and farm from fence to fence. That's one. And two, he disconnected the price of corn with the market by promising the farmers fixed subsidies for the difference between what the government thought would be a reasonable price and the actual price of corn. So what it did, it actually lowered the price of corn for the ensuing 30 years, essentially, by a factor of roughly 10, and the farmers were getting subsidies. Boots and the US government actually did another thing that resulted in the single largest jump of people on food stamp. They actually sold wheat and maize, corn, to the Soviet Union, which was falling apart at that time. And that was the single largest food sale in the history of the world. It resulted in at least doubling, perhaps tripling of food prices. And guess what? Countries that were in OPEC decided to double the price of oil as a result of doubling of the food price. And then came President, Ford, but then Carter. He started well, but then he had the Iranian conflict. So the amount of people, then we had 9% of population on food stamps. President Reagan was doing smoothly until the end of his 2 terms. The first President Bush, I guess, didn't do too well with the first Iraqi war, and he got fired. Then President Clinton did quite well, and when he was at the bottom, he passed the baton to the current President Bush. And he obviously is on his way up. And this is an estimate. I think we're going to exceed all records in the number of people on food stamps. So there are 2 conclusions from this slide. One, that today our efforts to burn excess corn as an agrofuel, in fact, date back to those efforts by Rusty Boots. And 2, it does matter what we do in agriculture to the general health of the presidents and in agricultural policy. I'm going to give you some very simple thermodynamics to the extent that I can. So the fundamental question that you need to ask is, okay, so I'm growing a crop and there is sunlight falling on the surface of the earth. What fraction of the solar energy that is falling upon that surface is then converted into grain? And I'm looking at these tiles here, sort of 3 by 3, 1 square meter, 3 by 3 tiles here, piece of land. And on average, the amount of solar energy that falls on that piece of ground in the United States is 200 watts per square meter. That's 24-hour, 365-day average. Okay? If you look at how much grain is being produced from the solar energy, on average, it's 0.38 watts per square meter. Each one of you is a 100-watt machine. Now that you're sitting and some of you are falling asleep, you're probably 50-watt machines. But if you wake up, it's going to be more. And so this is actually very little, not sufficient to feed us from many square meters, as you can see. Of course, corn has a higher average, about 0.5 watts per square meter. I'm going to use this. But the bottom line, that you will forget the exact numbers, for you to remember is that, in fact, the US agriculture, which is the most efficient agriculture in the world, really, sequester about 0.2% of the average US insolation, these 200 watts that fall on the surface of the ground. So this is not very efficient, yet we have to have it because we need to eat. So now let's compare apples with apples, because I want to make a comparison of sequestering solar energy and using it to do mechanical work. Now, I can do mechanical work by burning a fuel in a combustion engine, using essentially Carnot cycle efficiency. Or I can convert the solar energy directly to electricity, and I can then use electrical motors, which will convert into work with essentially 100% efficiency. So suppose that I have my corn grain, and that's 0.5 watts per square meter, and suppose that I want to burn it in the medium efficiency power plant with no district heat, I'm going to get about 0.2 watts electrical to power some machine, a rotating shaft. A very inefficient photovoltaic cell will sequester, let's say, 10% of solar energy, and you know that's really an understatement. And that would be about 20 watts electrical on average. And then, of course, if we charge the batteries and use an electrical motor, we're going to get some, 80-some% efficiency of conversion. So, roughly speaking, if that corn that we grew were burned to produce electricity, photovoltaic cells would be about 100 times more efficient than corn as a fuel. Now, a factor of 100 is, again, pretty abstract, but this is equivalent to me taking a jet, let's say to fly to Europe at 950 kilometers per hour, and me running at 9.5 kilometers per hour, and I wouldn't run for very long. I would die rather quickly. So that's a very significant factor. Now, if I don't want to burn corn, but I want to produce a liquid transportation fuel, then I have to deal with the efficiency of the agriculture ethanol cycle, which is about 30%. And I have to deal with, let's say, an average efficiency of a car, which is another 20%. So I'm going to sequester about 0.03 watts mechanical per square meter in terms of work of a rotating shaft. And that's completely, correct or not doesn't matter. It's the order of magnitude analysis. The answer here is that corn ethanol is actually a ridiculously inefficient way of fueling cars. So I'm going to go over crops now, food crops. There's going to be a couple of magical numbers I want you to remember. The first one is the mass of crops produced worldwide in megatons of dry mass. So all crops are on a water-free basis because different crops have different water contents, so I don't want to compare apples with bananas. The magical number is 700 million tons per year. Okay? This is how much it gets worldwide. And you can see that both wheat and rice have been increasing since the beginning of the Green Revolution quite significantly, but now they've stabilized, and they are all about 550 million tons per year. If you look at barley and rye, they're both declining and are much smaller, and potatoes held steady at about 100 million tons of dry mass over all these years. The second number, which is very important, is the crop area. And so here the crop areas are in millions of hectares. So 250 means 250 million hectares, or 2.5 million square kilometers. That's roughly a fourth of the area of the United States, including Alaska, okay, around 10 million square kilometers. So you can see that these crops take gigantic areas, each one of them. That's wheat, declining for many years, rice, pretty steady at 1.5 million square kilometers, barley declining, now steady, potatoes steady, and rye declining. If I now look at the crop yields, well, here seemingly there are some good news. So how many tons of dry mass will I produce per hectare of potato field, etc., in every year? You can see that these yields have increased, some of them at least doubled, maybe tripled. So potatoes, very prolific. The next one is rice, and then all the grains are about the same, and you can see they're kind of steady. And have been steady in their yields for the last 20 or more years. Now, the next number that is of particular interest to you is the number of kilograms of grain per living person on the earth at any given time. That's this number. As much as it gets, it's 100 kilograms. So that's what is at disposal of each one of us, perhaps sometimes in a given year, in terms of individual crops. So you can see that wheat reached that number some time ago, 18 years ago, has been declining ever since. Rice steady, now declining. all of them are declining, although potatoes quite slowly. So really, all the trends in per capita production have been declining. I'm sorry, I have allergies. Perhaps over the last 2 decades or more. Now I'm going to test if you're awakened, and I'm going to do the following trick on you. So I'm going to ask you, okay, so if you look at 1 hectare, I'm going to define what 1 hectare is in a second. How much food are you going to get out of this 1 hectare of some monoculture, wheat or whatever? So my daughter, who does medical research in San Francisco, photographed these 30 grains of salt, enlarged them. So this is actually, they're much smaller. I encourage you to spill some salt on the table, you know, from your friendly McDonald's or something like that. And so 5 milligrams of salt is 30 grains, so 1 milligram is 6 grains. Remember, 6 grains, okay? That's the characteristic value of mass you're going to get in any given crop from 1 hectare. Now, what is 1 hectare? When 1 hectare is a square of 100 by 100 meters, and it's difficult to visualize it. So here I stand in my favorite place, which is the Laundry Restaurant in Youngsville, Napa Valley, at the corner here. And if I go all the way from the street, all the way there, along the road, and actually back here, that's a little bit more than one half of 1 hectare. Okay? That's a little bit more than 1 acre. Okay? And you can see that all the guests are fed with greenery from all these little nice plants, which don't even fill that 1/2 hectare. So that's a lot of land. So now the question is, if I look at 1 hectare and I'm a statistical person on the planet, how much crop do I get in 1 year from that 1 hectare? Okay? And here the unit is milligrams. And so you can see that because the population is growing, the crop areas are declining, the yields are not increasing, then of course the per capita yields are all declining or at best keeping steady. So for potatoes, we will get an equivalent of 4 grains of salt. For rice, 3, and for all the grains, we will get an equivalent of 2 grains of salt. And think about this when you leave this room. This is a large area. When you look at it, it will produce a lot of food. But there's so many people that the amount of food you're going to get out of this would be these 2 or 3 specks of salt equivalent in terms of mass. Okay? That's not much. That's why we have so many millions of hectares of food-growing regions worldwide, and we have nothing to spare. All these trends are declining. So now agribusiness invades the tropics, which is the essential feature of agrofuel production. And I will quote first the classic from Stanford, Professor Somerville. And you can read this faster than I can talk. Essentially, what he's saying is that, well, production of agrofuel is happening, and since it is happening in the tropics, therefore, there's going to be massive deforestation of Indonesia, Malaysia, and the Philippines. And that's because it makes very good business sense to do this. And then he asks a rhetorical question, but is it worse for the environment, that deforestation, than climate change? That's the question. Well, to me, there's no question. Deforestation is the single largest driver of drying up earth and making it less pleasant for us to live. So to say that we burn the environment to drive more, and that's better than climate change, would be not entirely logical. And so let's go through the magical numbers here. 700 million tons of dry mass. You can see corn climbing up. It's going to hit 700 million tons soon. Followed by sugarcane, dry sugarcane, so this is sugar and bagasse only, soybeans, and oil and palm oil. So the rest of the fruits are not accounted for. You can see that the mass of soybeans and palm oil are actually increasing exponentially, and maize is the largest crop on the planet. Now, if I look at the areas of these energy crops, again, that's 1.5 million square kilometers, so that's roughly 1/6 of the area of the United States. Maize area is increasing. Soybean area is increasing exponentially. So is this. That's actually 5% per year. That's a lot more. And sugarcane is increasing linearly. And of course, all of these increases are coming out of tropical forests now, or most of them, and the pampas or savanna in other environments. And so how is it done? Well, we all know the story. This is a large forest fire in Borneo, photographed by European Space Agency in false color. So red is actually forest, green is the burned forest, and these are plumes of smoke. The unfortunate thing about Borneo is that it has lots of peat, has lots of swamps. These swamps have been drained and dried up, being burned, and emissions from one such event, let's say the 1997 El Nino event in Indonesia, was equivalent to all emissions of the United States in 1 year. Okay? So these are gigantic emissions which have global reach, which are being done in our name so that we can drive cleaner fuels. And there is another oil palm plantations being prepared for us in Borneo as viewed by the space shuttle astronaut. That's a very nice picture, of total devastation. This is a picture taken in Brazil by my friends from Greenpeace who are overflying a new gigantic plantation of soybeans, probably for Cargill. You can see this huge tractor with a sprayer, probably spraying glyphosate for the Roundup-ready soybeans. There's this one tree left, which is a Brazilian nut tree. By law, they cannot cut it, so they just leave one tree on thousands of hectares of land. If you look at the yields of these energy crops, now you know why people like sugarcane. It is by far the most prolific plant. Its yields are, on average, worldwide, are hitting now 20 tons of dry mass per hectare. That's why people love it. If you look at corn and palm oil, they're about the same, about 4 tons of dry mass per hectare per year. The US agriculture in corn agriculture is twice as efficient, 8 tons per hectare. Okay? So we are a factor of 2. And you can see soybeans are the smallest ones, and in fact, their yield has been declining. Now, this is not by happenstance. These new Roundup-ready varieties, in fact, are so Roundup-ready that they forget to produce soybeans. And so the yield, in fact, is not increasing. And if you look at per capita production, again, 100 kilograms per person per year. Corn is getting there. It's going to get there probably next year. Sugarcane, steady now. Soybeans, increasing. So is palm oil, also increasing. All trends are increasing. If you look at the per capita yields, they're actually quite high, higher than those. So you get 18 grains of salt equivalent per person per hectare per year of sugarcane, 4 grains equivalent of salt of oil palm or palm oil and corn, and 2 grains equivalent of salt from 1 hectare of soybeans. And these trends are steady for the 3 plots downstairs and decreasing for sugarcane, whose area is not increasing exponentially. So now I want to spend a little bit of time telling you why I think that the green revolution as we have implemented it is failing, and it, in fact, is going to continue to fail at an accelerated rate. So I cannot do justice to this plot produced by my friend Robert Ulanovich, an ecologist from the University of Maryland, who applied information theory to quantify information content of species and information exchange among species in an ecosystem, and then came up with an entropy-based function, which he called sustainability, which is the ratio, let's say, of efficiency to efficiency plus resilient. It's a logarithmic function which is scaled. It scales between, let's say, 0 and 1. And here's the point that I want you to remember, regardless of the whole mathematics. Ecosystems put a huge premium on resilience. And resilience is diversity, many species present, and redundant interconnections. Ecosystems at the same time have to have certain efficiency or streamlining because they have to survive. They have to propagate themselves. And so If you look at efficiency, that's everything that we pay attention to. If you look at the US airline industry, you have a perfect example of an industry that is very efficient, extremely streamlined, and absolutely not resilient, breaking at the slightest difficulty with catastrophic reverberations worldwide. And in fact, this is exactly the same thing that we're doing with agriculture. So it turns out that normal ecosystems, the ones that grow in nature, have this optimum, and we push our monocultures that we drive with fossil fuels to the right of this optimum, perhaps even lower than here, because we value efficiency, crop yields, much more than sustainability and then resilience. And that's going to come back to haunt us. In fact, it has already, big way. This is one of the scariest plots that I can show you. It doesn't look so scary, but it is. And it comes from my friend, Ken Kassman, who's your typical sharp scientist who's very much inside the system of the current agriculture. So he's not advocating anything of the sort that I'm doing here. However, nevertheless, he does work which is very good, and that's one of the plots that he produced with some co-authors. So this is kilograms of grain produced per kilogram of nitrogen applied at various parts of the world since the beginning of the Green Revolution. And you can see that in the beginning in Africa, when you had local crop varieties and fertile land many years ago, you put some fertilizer and the response was tremendous, 150 kilograms of grain. And then, of course, with time, it declined. If you look at the developed world, Western Europe and the United States, well, we've been applying fertilizer for quite some time, guano first, then nitrogen. So there's not much response to that. If you look at Eastern Europe, primitive agriculture first, then collectivized, very inefficient agriculture. This is the fall of the Berlin Wall. Unleashed agriculture and productivity, now it's falling back on the same trend. If you look at the whole trend of the world, the thick green line, you can see that in fact all parts of the world now have fallen onto that trend. And that trend is actually quite unsettling. It says that you're going to get about 26 kilograms of cereal grain per kilogram of applied nitrogen, and it is declining at 4% per year. And so essentially what we're doing here to increase the crops, and again, don't get me wrong, a lot of progress has been done through better hybrids, better plant varieties, but a lot of it is done through application of fertilizers and field chemicals, okay? And these are monocultures which are incredibly susceptible to pests. Now, in terms of US agriculture, that's my own data, USDA's data that I plotted, you can see and I plotted them, you can see that both nitrogen in red and phosphorus in elemental quantities are applied by science in identically the same quantities, and the response is twice as much as the world average, as I just told you, about 52 or 55 kilograms of grain per kilogram applied of phosphorus and nitrogen. Potassium is a different story, but it's now also about stabilized. And if I look at the response of US agriculture to all of this, better hybrids, more fertilization, better farming techniques, you will see that from the plowing of the prairie till today, we have had a tremendous increase of efficiency in terms of bushels per acre per year. That's the only time I'm going to use these units, only because in numerically, they are equivalent to gigajoules per hectare and per year. So that's why I use them. So 1 gigajoule per, so 47 gigajoules per hectare is equivalent to producing a high heating value of 1 ton of gasoline. So this is 1 ton of gasoline. So our fields now are producing equivalent, if you were to burn the grain, of about 3 tons or 2.5 tons of gasoline per hectare per year. And you can see if I fit the data with logistic growth, that thing is going to stabilize about 160 bushels per acre per year. If I do the best fit, and if I'm optimistic, maybe 200. Either way, we are getting to a plateau, which would be expected by the limiting efficiency of these systems. And this is a 204 plot. We have never reached that crop. We have never reached that elevation again, and will not reach it this year as well. So I might say that we are getting pretty close to a plateau of the US agriculture. Yes, I will not finish. As I said. So I'm going to give you just two more examples and do a summary. Most of increase of efficiency of the agriculture was achieved by breeding new hybrids, whether by conventional breeding or by genetic modification more recently. But here's the story of the hybrids. Suppose that I want to reach a yield potential, that is as much as I can produce from a given plant. And let's say that at the beginning of the Green Revolution, I produced my first hybrid. And then, of course, pests would evolve, and it would be killing it better and better. So its yields would be declining with time. So then 5 years later, with great amount of research and industry, I would introduce another hybrid. The same thing would happen to it. Then another one, another one, another one, and yet another one very recently. And so, in fact, I have not increased my yield potential at all, but I'm getting higher yields only because they are newer to the pests. If I do a look back in time, so plot, let's say in 2005, how do all these hybrids perform? Obviously, this one is right here, and the most efficient one, the recent one, is at the top of the insert. And you can see that then I get a warm, fuzzy feeling of having increased efficiency of agriculture, while in reality, I have done nothing. I have been running ever faster to keep still, and I have not increased performance of these hybrids. I have just generated new bugs. Now, in soybeans, in fact, the story is even worse. So with time, my yield potential is, in fact, decreasing. So that line, that look back in time, from the oldest to the newest hybrid is in fact curving down, as we were seeing from the world data. I will show you briefly the food prices. So these are global food prices in US dollars per ton, starting from corn in October of 2005 going, let's say, to May 1 of contract of 2008. And this is Chicago Board of Trade, so I mixed two types of data. Corn, $100 per ton in October 2005, reaching $246, $6 per bushel in May 1 contracts, going up to $8 probably in the fall. Wheat, $175, going all the way up to $450 roughly dollars recently. Rice, $300, increasing slowly. Then I thought that I made a mistake plotting the Chicago Board of Trade data, so I just plotted India contracts from some other source at $500 per ton, but then I was shown to be wrong. These numbers were actually correct. So the contracts on rice are now reaching $800, $900 per ton. And in fact, since many countries have stopped exporting rice, Vietnam and Thailand being two of them, this price perhaps is not going down anytime soon. If you look at world food price, where the 1998-2000 price index is 100, then it is no surprise to you that in the last 2 years or so, we have seen tripling of dairy prices and then essentially doubling of prices of other products other than meat. And remember, FAO data stops here in the third quarter of 2007. If you go to your friendly supermarket now, you will see that that chicken actually costs twice as much as it did in the last quarter of 2007. So the price of meat actually has gone up as well. So we are seeing actually food price hyperinflation. And that is inflation of 100% or more in a very short period of time, which is beginning to hit everybody in the pocket. And of course, we are rich. We are actually filthy rich, and so we don't have to worry yet. But in the poor countries, the ones in which most people live on $5 or $1 per day, they are maybe still getting nutrition. Somebody will drop a bag of rice on their head from a helicopter, but they will not get the proper nutrition. Micronutrients. So you have now stunted growth in children. That will then be followed by lowered intelligence of whole generations of children worldwide. Their misadaptations to workforce, to learning. And so we are seeing a global catastrophe in terms of food supply. And of course, this is not being mentioned too often. I will skip the switchgrass. There's a beautiful story in which I could show you that corn ethanol actually looks pretty good compared to the switchgrass ethanol, but not the point. I will publish a paper soon, you'll see it. But I will finish with 2 points. First of all is that currently photovoltaics of the major classes, such as monocrystalline silicon and polycrystalline silicon, and also the CIGS process, are all reaching 20% efficiency, and I use 10% efficiency in my calculations. In my OECD paper, I also charge photovoltaics with 30% of the lifetime production of electricity to make them, which is conservative. And you will see that in a more detailed analysis, they do very well compared with agrofuels. And so just to remind you, this is 1/2 of a hectare. And if I were to produce cellulosic ethanol from 1 hectare of switchgrass field, the work that I will do to move a car is equivalent to these 4 square meters of photovoltaics on my roof. And these are the 10% photovoltaic cells. So the point I want to imprint upon you is that we are reaching perhaps not at the best technological solutions. Better technological solutions definitely are within our reach, but we have to kind of snap out of it and reassess our priorities. And one would be to reassess the urge to drive and the urge to consume energy, which sort of is driving this country in the bad direction. And I wanted to do another quote of Dr. Somerville a year later. That's actually kind of an interesting quote, because he's basically saying that now that photovoltaics are no good compared with cellulosic ethanol because plants are so abundant. But I would dispute that claim as well. So in conclusion, I think that there has been a systematic breakdown of democracy, science, and here at Stanford, I should stress that element, science and common sense, in dealing with the global food supply and energy production. And as a result, extreme hardship to an ever larger number of poor people and the destruction of the lungs and kidneys of the planet, these very large ecosystems that are being destroyed now, today, in real time, as I'm talking to you, have been the result. And what I encourage you is don't sit here, don't smile, or don't frown, do something about it. And start from yourself, but also try to write, your representatives' protests so that you do not become what I call hapless victims of other people's delusions. And when I made this comment in front of a lady from South Central LA who was fighting to have some city gardens for the poor people, she said, "Funny you should say that, because I was using exactly the same argument when I was talking to the city council." Don't wait for others. Do something. Try to start growing a little bit of food in little piece of land or in pots or something, but get used to the idea that, that you're not going to have all the food available, and that which will be available may not be of the highest quality. Now the plaque. So remember that bear behind the barbed wire? So in front of it there is a plaque, which is actually, I find, very timely. Fight for California. And it says, "Our sturdy golden bear is watching from the skies, looks down upon our colors fair, and guards us from his lair. Our banner gold and blue, the symbol on it too, means fight for California through and through." And this was written by a classmate of 1909 when this plaque was funded and the bear. So with that, I would like to thank you, and hopefully you're going to ask me some tough questions. Thank you very much. Yes?
So you show trends over 40 plus years, but the food crops are only used for energy production for probably the last 10, 5, even more.
Yes.
How much of the energy crops are actually currently being consumed for energy versus food?
Right. This is not the point I was trying to make. I was trying to take out the effect of population growth. Remember, the 800-pound gorilla I have not spoken about is the rate of population growth in the world. So that was there, lurking in the background. I was dividing the increase of crop masses through an ever-growing human population. Okay? And so what I'm trying to tell with this story is the following. regardless of whether we have energy crops or not, all ecosystems that we have converted to work for us very hard are being stretched to the limit. In fact, they are becoming insufficient to feed us. So therefore, diverting even more land and encroaching on other ecosystems is actually now double jeopardy. That is actually really a dangerous, dangerous thing we're trying to do to this planet. And the most unfortunate thing that is happening is that in our name, in your name and in my name, people are going and burning forests today in the Democratic Republic of Congo like there were no tomorrow. In Indonesia, Myanmar has been plundered by the Chinese left and right because they are not cutting trees in China, but they need lots of wood, right? And Malaysia is making investments in Indonesia because you cannot cut with impunity and burn things in Malaysia, but you can do so on the Indonesian side of the islands. So the same thing goes for Uruguay, for Paraguay, for Argentina, for Brazil, for Bolivia. Have I named enough? And so what you're seeing is, in fact, destruction of the last large contiguous ecosystems on this planet. And since many people here do climate modeling and know better than I do, is that deforestation, in fact, has been the single largest force behind climate warming and unpleasant climate changes for most humanity for the last 15,000 years, because it hasn't started today. China was deforested 5,000 years ago. And so I guess my really message to you is, watch out, because this planet has no spare capacity to do more things for us. It's time that we, as elements of this planet, not these super creatures, right, who can do whatever we want to Mother Nature, we have to take notice. We have to understand that we have reached the limit. And when we have reached the limit, that means that a new shiny highway should not be built. And we should not be adding yet another neighborhood on a steep slope. And many other things should not be happening that are, because we are pursuing an absolutely false paradigm of modern economy, which essentially says that Mother Nature is worthless so long as we don't use it. And when we use it in a closed cycle, which comes from the production to consumption. And then there's two things, and it's a closed system. It just takes things from the environment, and then they become valuable. And then it dumps things into the environment, and then they become worthless. And the environment can accept any amount of dumping, right? And that system is, in fact, growing exponentially because that's how we have constructed it, right? Yes?
I was wondering if you might comment on waste product.
Yes. Okay. Very good. So the point that I'm trying to make as a chemical engineer, somebody who does thermodynamics, is that in fact the planet Earth and Mother Nature know of no waste. Waste does not exist. Okay. And the reason is actually very simple. It comes from the fact that our planet functions supporting life because of two things. One, that there is sun, which actually gives us high energy photons. And then two, we are an open system with respect to infrared radiation. So we are essentially a photon multiplier. We are satisfying the second law of thermodynamics and throwing out a lot of low energy photons into the cold universe. And that flow of energy has actually resulted in life. However, all mass stays on the planet. In fact, even hydrogen stays now on the planet because life has evolved oxygen and then ozone, and ozone reacts with hydrogen and dumps it back as water. If all mass stays on the planet, then all mass has to be recycled. Otherwise, it becomes a waste product that will poison and destroy every ecosystem on the planet. And so therefore, one species waste has to become another species food. And that's how Mother Nature works. And what we do as humans, we cut all of these eternal cycles, and we say from here to there, we're going to move on a straight line, and there's going to be lots of waste. Well, to the extent that we can live sustainably, we're going to have to go back to cycles, and most of the waste will disappear. Yes?
There's one slide where you show the comparison between switchgrass and the solar energy density.
Yes.
I thought that was very interesting. There's a lot of talk these days about biofuels and how it's a growing industry.
Yes.
Do you see any sort of biofuel that could compare to solar power in terms of energy density?
No, no. The answer is clearly, emphatically, never. It just cannot be. The reason is that you are going through a very complex process that reacts to very different factors that work, or drivers that work in opposite directions. And plants over the last 3.5 billion years have evolved photosynthesis and evapotranspiration in such a way as to optimize their performance with respect to all of these factors. And that performance results, in fact, in that 0.2% of solar energy being transformed into useful grain, and another 0.3% into stalk, leaves, and roots. And so if you look at the entire net ecosystem productivity of the United States, it is less now, today, than the amount of fossil energy that we're using every year. And of course, all of this net ecosystem productivity is accounted for one way or another. And so we are now beyond of point of no return. Something's got to give, okay? And what's got to give is our energy use. We have to use less energy. And when I say less, let's not beat the bushes. Factor of 2 just to get started. That would bring us back to Sweden and Western Europe, who live at much worse climate. And then another factor of 2 when we actually put our minds to it. And so we're going to have to rework the whole infrastructure of our society, how we commute, where we live, how we eat. Local agriculture has to happen. We cannot be driving and refrigerating everything for thousands of miles. So many things will have to change, and we better get started now, but that discussion is not taking place. Instead, we are being told every second day that there is another magical solution that will save us. And especially for people who were born here, the word technology has this religious connotation. Technology is something that's going to be good for us, it's going to save us. Well, let me tell you what I think. Many of the problems I have been talking about today have no technological solutions. None whatsoever. Because we have gone beyond the carrying capacity of the planet, and there is no technology that will reverse that. And so we're going to have to do things differently. One would be to decrease the number of humans or grow more slowly. That would be also very good. Okay.
All right, let's thank Ted. Okay, so remind me next week, fuel cell.
But no food this week. This is the only week that I have to go to work. Very good. Question.
Yes.
Lots of your discussion, you were talking about grains to fuels.
Yes.
But if you ask Chris Somerville, he would agree with
The preceding program is copyrighted by Stanford University. Please visit us at stanford.edu.